Um, yeah, so I think a theme in some of these talks has been sort of how we go out from programming languages into other areas and take those ideas and then bring them back in. And so hopefully you'll see some of that in this talk. I started working in programming languages when I was, I think, 14. I wrote an interpreter for a language called Pilot. And basically, this area has fascinated me ever since. And so it's really kept me excited for my entire career. But 5 years ago, when I went to Google, I said, okay, I really don't want to keep working on the same thing. I want to do something in the area which is Google's sort of core technical DNA. Every company has this sort of fundamental thing that drives the technical culture. And at Google, it's these huge distributed systems. So I asked for a mission, and for my sins, they gave me one. So I work on Spanner, which is Google's distributed database system. So Spanner is a planet-scale database. It's replicated for distribution and availability and for performance. So you can have replicas in data centers across the globe. And it provides, for the first time, externally consistent or ACID semantics at global scale. So you can write transactions, commit them, they get committed to all replicas, and we provide consistent answers for queries anywhere in the world. Part of the magic behind this is the fact that we have highly synchronized atomic clocks in all of our data centers. And so basically, within the error of those clocks, we can infer happens before relationships without having to exchange messages. In some sense, you could say I've never left programming languages because, in fact, Spanner just implements the SQL database. So what I'm really working on is the runtime system for yet another programming language. And of course, since we're constantly writing data, and many of Google's systems have this architecture that they don't modify in place. They sort of write data out, and then on the other end, it gets reaped over time. So you could also say that I never managed to escape working on garbage collection. The volume that Google operates Spanner at is enormous. We are managing hundreds of petabytes of data. We serve hundreds of millions of queries per second. And the other aspect in which we're growing very rapidly is in terms of the number of databases. Originally, Spanner was developed pretty much just as databases were in their infancy, right? The whole transaction concept comes out of banking. If what you're storing is money, you don't want to have lost updates. And Spanner started out its life at Google supporting the ads and payments infrastructure. And Google pioneered the whole NoSQL concept where we said, okay, well, we just need to scale at all costs. We have no technology that lets us, do SQL and consistency and so on. And so the whole NoSQL unstructured, non-consistent kind of scale-out system was born. But over time, we've managed to figure out how to solve some of these problems. And also, we've figured out that everybody really wants consistency, right? And everybody winds up implementing kind of the consistency that they think they want. And that takes an enormous amount of effort. And often because their bread and butter is not, implementing various forms of consistent semantics, they get things wrong or they learn hard lessons along the way. So Spanner, internally to Google, I think of our mission as organizing Google's information and making it accessible and useful and durable and secure and private. And those two things have, of course, in the last decade become more and more important and, in fact, drive many of the challenges in terms of the computer science problems that we're facing. I think that's a really interesting area to work in. Spanner runs as a service. So we just have servers running in data centers all over the world and supports many of Google's multi-billion user products. So here's an example of a system that you probably didn't know you were using. It's called Zanzibar. And this is our access control system. So what I'm presenting to you is slides in Google Slides. And I've shared them with people, right? So if I send you the link to my slides and you click on it, the first thing we have to do is say, well, is this person actually allowed to look at this document? And that's done by making a call to the Zanzibar system, which manages these access control lists. And of course, Zanzibar is a big, complex system in its own right, but underneath it all, it's implemented on top of Spanner. And so these queries eventually turn into queries to Spanner. And these queries have to be done at global scale. And of course, the kind of consistency that we offer is extremely important because it would really be a fundamental failure if I revoked Jens's access to my slides, but then after that he actually managed to access them, right? So we don't want him to be able to take advantage of some 100 millisecond round trip latency or something like that. As you can see, even for this system serving a huge number of users, it can keep a weekly 95th percentile latency below 10 milliseconds, and even at the 99.9th percentile, it's below 100 milliseconds. As a database for mission-critical systems, the most important thing for us is our availability. And this shows Zanzibar's availability running on top of Spanner over the course of 3 years. And basically, they've managed to maintain 5 nines for over 3 years. 5 nines means you're up and running 99.999% of the time, which means you can be down for exactly 5.26 minutes every year, which, if you're lucky in 5 minutes, an engineer might be able to notice that something's wrong, much less root cause it and fix it. And the kind of layering of systems on top of systems where you're trying to get to this kind of 5 nines reliability at the end user system, right? But those end user systems are then implemented on multiple systems like Spanner and Zanzibar and the Google file system and so on. So the availability demands on these systems are enormous. About 1.5 years ago, we launched Spanner as a cloud product. So we're trying to make this kind of planet-scale SQL database universally accessible. That's been really interesting, and it brings with it a whole host of other problems, right? At Google, one of the advantages that we have is, if there's something wrong with what's going on in another service, I can instantly go and look at the source code where they're calling it a spanner, and I can get in touch with their site reliability engineers and say, hey, could you stop sending this much traffic to this zone. With cloud customers, we can't do that, right? We have to have a much more turnkey system. We can't expose so much low-level information, and that is a whole added complexity, right? For our external users, the names of the databases and the tables are hidden. We don't even get to know what those are named. So the thing that I've been working on since I joined Google 5 years ago, I jokingly call this my starter project. When I went to Google, they said, oh, we're doing this new storage engine for Spanner. I said, great, I'll work on that for a year, I'll launch it into production, and then I'll figure out what to do next with everything I've learned. Turned out that I was a little naive about how much work was involved. So Ressi is a new storage engine for Spanner. Spanner started out effectively forking the Bigtable code base, right? So that let them get up and running much more quickly because they were able to concentrate on the unique sort of distributed systems aspects of providing consistency and so on. Initially, Spanner didn't even have a SQL interface. That's something that developed over time. In general, SQL has been something that has grown steadily in use at Google, maybe a little bit like the example of regexes from Unix. So initially, all of these systems had low-level custom APIs, and then one person after another said, gee, my friend told me that there's this thing called SQL. I wonder if we could use that here. And they would build that, and then we wound up with this multitude of SQL dialects, which have then been standard and so standardized within Google. Anyway, so that architecture was oriented towards unstructured NoSQL data. And that data format has to be self-describing, so it's highly redundant. So it then has to be run through very aggressive compression algorithms. And it's frankly kind of amazing that it's survived so well, and the performance that's been obtained out of it has been so good. But at this point, we're kind of reaching the limits of that technology, and so Ressi was designed to provide a new modern base on which to develop and innovate the system. So, it's native to SQL. It's strongly typed. I hope everybody here is an advocate for strong typing. And one of the important things that it does is it separates the old versions of data from the latest version. So one of the ways that Spanner achieves scale is it keeps multiple copies. If you write the same data item many times in a short amount of time, all of those versions will be kept. And in some cases, you can do a less expensive query by saying, what I'd like is a consistent view of the database 2 minutes ago, right? And that's less expensive than saying, I want a consistent view now. So basically, we store version timestamps in the database. Now, that has the property that, generally speaking, if you do an operation over the database, that will be big O of the number of things you've written into it, not big O of the number of things that that are logically in the database. Back when we had just a small number of customers, that was okay. People sort of, we could explain to everyone, that this is how the system worked. When you have 5,000 different users, they just kind of want it to work, right? You can tell them till you're blue in the face, but people are always running up against this problem. So one of the themes over time has been, just as Spanner has kind of allowed our client systems to delegate all the work of consistency and replication to Spanner, we're also letting them, we're sort of handling various kinds of complexity and then shielding them from it. So, our goal is to get to a point where an operation on n data items will just take O of n no matter what, right? Just because that's just fundamentally simpler for people to reason about. And if we can push that complexity into Spanner, then nobody else has to deal with it. So another fundamental thing that we've done is we represent the data in these things we call vectors. And so for each data type, we have multiple data representations that do various kinds of compression that are suited to the data in that column. And the key thing there is that most of these formats can be accessed directly in their compressed form. So we never have to, read a block from the disk and decompress it. And in some cases, we can even do key lookups and comparisons entirely in the compressed domain. If you asked one of the people who works on other parts of Spanner, the boxes here would of course be in different ratios, but here you have the three replicas that you saw. These are individual servers, so a slice of a database called a tablet exists on the three servers, and each tablet is made up of layers of data, almost like sort of geological layers over time. And what Ressi has done is basically, to a first approximation, re-implemented that layer interface. When you do writes, they come into these mem tables where we make use of lots of cool lock-free algorithms so that we can have very high concurrency on the writes. Eventually, when those fill up, they go through compaction and compression. They're then written in this vector form to a cluster file system. So we have the three-way geo-replication within each local cluster. The files are also redundantly encoded using Reed-Solomon coding, so we can tolerate the loss of disk blocks from the file system. You could just take out the entire data center running this replica, and we would still have a majority of replicas and be able to continue serving reads and writes. Once the data is written out to the cluster file system, we have a flash cache that we put blocks into. We have a RAM cache. So all of these various components are basically responsible for the bulk of the resources consumed by Spanner, other than the networking, right? This gray communication area is where all the networking cost happens, and that's above Ressi. So one of the things that really surprised me when I joined this project, and sort of over time, took me a while to appreciate over time, is that we have to live migrate the entire hundreds and hundreds of petabytes corpus to this new data format while maintaining all of our availability guarantees. And while people are writing distributed transactions and moving entire replicas between clusters, and while tablets are being split apart because they're under heavy load and so on. And we have to do that without, for all of these many, many different systems, each of which has its own peculiar n-dimensional performance shape on top of Spanner. And if we make things worse in any single resource dimension that exceeds their quota or the capacity of that cell, we could cause an outage. I would say this has consumed probably 1/3 of the entire engineering effort of this project. We were actually very lucky that one of the people on the team figured out that we could piggyback on an existing mechanism that already solves this problem, which is the process that lets us move replicas or add replicas in other clusters. And so a change in format we represent as a cluster move, except that we just move to self, and as the data is being moved, it gets rewritten into the new format. But this is a problem area that I'll come back to, right? The good old days of sending out an email and saying, at midnight on Friday, we're turning off Gmail, enjoy a nice weekend, and everything will be back on at 6 a.m. Monday morning. And so I think this is just a new reality of computer systems and an area that's kind of ripe for innovation, because that anything we could do to reduce that engineering of this recurring problem, I think, could be enormously impactful. So what's so difficult about building this system? I think it's really amazing how robust Spanner's overall architecture has been. It's scaled by many, many orders of magnitude since it started. And to a first approximation, that the growth over time and scalability has been sort of finding places where early on we said, oh, well, this particular data structure or this piece of metadata or whatever we can allow to be centralized or to be monolithic. And then, when things are 1,000 times as big, suddenly that's no longer the case. Kind of reminds me of what, when I was working on garbage collection, first we made the marking phase incremental, and then that wasn't good enough. You make the sweeping phase incremental, and then you make the snapshot at the beginning, and then you make the termination incremental. So there's always one more thing. Each time you want to push the envelope, there's kind of the next frontier of things that you make scalable. And of course, there are many, many fascinating technical subproblems there, but this isn't a database conference, so I won't go into those. The thing that's really hard is programmability, and the programmability of a system that is under enormous pressure because we have to provide a very high degree of reliability, and yet we have an enormous amount of demand for features, and we have a growing set of users doing different shapes of operations, and the scale is growing. So, I've talked already about this kind of theme of trying to shield all of the many users who are building on top of Spanner from complexity and trying to prevent many, many implementations of workarounds of the same problem. So that's something that we spend a lot of effort on. And then the other thing is this internal growth and complexity. So one of the things that I found is that, at scale, every pathology that is latent in your system anywhere is going to happen sooner or later. And I've learned to become very wary of the word surely. So, at one point we were trying to figure out how to represent all of these timestamps for the deleted values. And I said, well, surely no one would delete the same thing more than 1,000 times in an hour. And so let's give ourselves a massive amount of headroom. We'll multiply that by 10,000. And then we can use a fixed data structure, and that'll simplify so many things. And of course, simplicity is really important. And of course, that turned out to be a horrible mistake, which we found out when the system reliability engineers started instant messaging us saying, hey, you've got servers crashing over here. So we had to go make the code more complicated and break this up. So basically, no. Another example was, it was a similar kind of meta pattern, right? Each file in the database has an index, which is basically a tree of blocks, and you can just make the code much simpler if the root of the tree is always there, right? And so, we sort of did a calculation and said, okay, well, the root on average, the block is maybe 16 kilobytes, and oh yeah, no problem. And that worked great for many months until one day there was a sequence of conditions. There was low availability in a cell for disk IOs, and there was our prefetcher wasn't doing a great job for a certain kind of workload, and so suddenly the amount of space available to the cache started to shrink and shrink and shrink, and suddenly those blocks, which used to consume 1.2% of the cache, were consuming 50% of the cache, and now things entered this kind of death spiral where we had less and less memory, and that caused us to do more and more I/O, and there was no I/O available. And anyway, so I think I've learned that I used to be an unbelievably sloppy programmer and system designer. I don't think I ever realized the extent to which, when I was writing code and building systems, that I was kind of making all these implicit decisions as I went along to kind of just not deal with a certain kind of complexity in the favor of keeping the system simpler. Avoiding and preventing these pathologies is a huge part of what we do, of what we spend engineering effort on. And sort of a related thing is that at scale, kind of all bugs seem to happen, right? If you can have ultra reliable components, but the more of them you have, the more likely any particular bug is going to occur. And of course, you've got layered systems, so there can be a bug at some lower level of the system, and if that's an unusual condition that you haven't bothered to handle, then that bug is going to infect your code. So you could sort of think of, from a software engineering point of view, you could think of Google's data centers as kind of an enormous fuzz tester. And the kind of the impact of that is that if you have a system whose deployment is growing linearly, you've got to make the components better linearly just to keep up in terms of your reliability. Now, luckily, many things we do in software engineering are super linear in terms of improving reliability. But now if your system is growing exponentially, you've really got to work very hard just to tread water in terms of the reliability of the system. So as a result, Spanner is one of Google's largest users of test resources. And we just do all sorts of testing at many, many different levels. It was, of course, painful for me, having worked for 15 or so years on garbage collection, to go and work in C++. But this is a lot less miserable because of all of this testing infrastructure. So these sanitizers are continuously running in the background, looking for addressing violations and dangling pointer violations, and things where you relied on something not overflowing that might overflow or whatever. We also have customized system tests where we basically bring up an entire Spanner universe in a real cluster, and then just for 24 hours we take replicas down, we turn off access to the encryption service, we insert corruptions into the file system, and so on. So trying to probe as much of that attack surface as you get in production as possible. Testing tools, very, very important. Much, much work yet to be done. Performance, of course, matters, as it always does test, but it matters kind of differently. So one important difference is that things that would be that I would have in the past considered in the noise and not worth doing and not publishable, like a 0.1% improvement, actually, when you scale them out, turn into lots of money, and so they're very worth doing. But the hard part is actually having the ability to measure it, right? So how can you implement something that's a 0.1% performance improvement and reliably measure it, both as you're testing and developing and in production? So Amar Dewan has a paper on measuring systems in production, which gives a really interesting perspective on this. But the whole area of measurement methodology, I think, is something where there's still work to be done. And the other thing is that we care just as much or more about edge case performance, right? Like the example of the cache blocks being pinned, right? It's in that case, it actually meant what we did just made there be more memory available generally, so it was good in all cases. But often you wind up having to make some kind of trade-off between, can you maintain this performance at the 99th percentile if you give up, 10% at the median. Something that I learned as a hard lesson over several years, it's both a blessing and a curse at Google that we have this single code base and everybody can see it. And I actually had, I remember getting this email from someone on one of these product teams, and he said, "Hey, I found this bug in your system." It was in a part that I didn't even understand, but I fixed it and sent you the change list. So, that was really quite amazing and wonderful in many ways. But the flip side of that culture is, you'll also get email from someone saying, hey, I noticed you have this hard-coded constant in here, and I checked out your code and I changed it to blah, and everything runs much better, and I figured out that this is going to reduce the total cost of ownership of our system by X million dollars. Could you give me a little flag or option to control this? And of course, it's very hard to say no to that, right? Because it just seems like, wow, Google is a very quantitative kind of place, and it's very hard to say, no, you can't save X million dollars because I don't like it. And so you kind of have to see over time the impact of these things. And so the fundamental problem is that exposing some tiny little tuning parameter like that can turn into a massive amount of technical debt, both for you and for the customer, right? Because once they've tuned this, right, now they're running in production with 1 billion users, and you say, hey, by the way, we found that this parameter isn't really helpful, so why don't you just turn this thing off, and we'll do great. You don't need that anymore. And I said, well, yes, but then we'd have to write a whole bunch of tests to check that, and then we'd have to do this gradual rollout in production, and so on and so forth. And so there's this huge inertia because there's a very real cost to validating that you can change this. And so, and then that in turn starts constraining your system in one place after another, that you can't change this and you can't change that, and you can't sort of couple these two things together. And so that's the accumulation of those little quantitatively rational decisions are actually can become kind of a long-term architectural disaster. So I've spent a lot of effort on trying to take away these tuning parameters that have been exposed for the old system, and provide new ones. So, well, I see I'm running low on time. So, so we have ways of filtering accesses to reduce I/O that used to be controlled manually, that we now do self-adaptation internally. We just measure the system and turn them on and off. And we're also automatically selecting the best vector implementation to represent each column instead of letting people set these themselves. I'm going to skip these. Okay. Right now, I think the biggest single challenge that we have is that we are trying to do computer science and systems work on data that we can't see and we can't keep, right? So if we want to do, the classic bread and butter optimization, get 5 database files, copy them into your, into some subdirectory and write code and iterate and speed things up. That's just not something we can do at all. All of that data is encrypted, and the bar to being able to look at that data in a production emergency is enormously high. So figuring out how we can do good performance analysis and development without having access to the data is really difficult. So, you know, there have been these approaches like differential privacy that have been proposed, but it's difficult to both keep the properties of the data that will give you realistic performance, and also, as people have shown, you know, it's easy to make mistakes when you're trying to obscure the data. So there's a whole area of work, I think, here that could be done to come up with a sound methodology of doing performance analysis on encrypted data. I talked a bit about this before, upgrading with zero downtime. This is both in the small, like when every 2 weeks or so, we push a new release into production. You know, being able to do that without having to restart the servers or finding ways to provide linguistic or library support to do that easily would be an enormous benefit, because every service has this problem in one form or another. I can't leave without saying something about memory management. You know, for a system like Spanner, garbage collection just is not practical to use given the memory overheads that it needs. So now, using malloc isn't free. I guess that wasn't the right way to say that, but anyway, you know, there's a significant fragmentation overhead that you have to live with. So it's not that there's zero memory cost, even if you're very careful about that. But you know, what we wind up doing is we use Arena. You know, we find, oh, this piece of the code is causing too much fragmentation, so we convert that to use arenas and so on. But you know, when I left, I thought, oh, this is such a totally when I left IBM, I thought, oh, this is such a totally mined out area. There's nothing interesting to do here anymore. I think actually there is, and you know, languages like Rust and research ideas from languages like Cyclone are still areas where I think there's interesting and impactful work to be done. And finally, you know, verification and proof of correctness. The great thing is that, you know, for the research community is that the more costly bugs become, the more economically sensible it is to invest in verification technologies. We just spent 7 months finding a bug that you know, was occurring like once every half year. I wound up putting myself on pager duty and waking up at 3 in the morning and, you know, copying files before they went away so we could debug the thing. I'd much rather have good verification technology. And I think both, you know, starting with things like find bugs, pioneers sort of looking for small bug patterns, and then kind of growing that, as well as, you know, the kind of progress we've seen in systems like Coq, but finding ways to integrate that into, you know, a massive scale system where the reality is there's still going to be a ton of C++ code, and we need to find some way of modularizing the verification of the most critical parts. So I think I'm over time, and it's lunch, so I will stop.
Fascinating talk. What are you not storing in Spanner? So are there types of data that are not worth or efficiently storable in Spanner?
Oh, sure. I mean, so a lot of systems, for instance, will store metadata in Spanner, but will store data just in the regular file system. Logs are an example of that. So yeah, lots and lots of systems don't need Spanner for that.
Hi, David. You mentioned programmability as a challenge. Can you say a few words what the programming model looks like today?
I'm sorry, what?
What the programming model looks like today. So, since you say programmability, I assume it's hard, the programmability. So, what makes it hard?
Oh, I mean, we're using, C++ with, stylized, unique pointers and ownership and, all sorts of best practices. But, I just meant in the more general sense that, the programming of the system is just enormously work intensive. And, we need, having better languages and better tools and all of that stuff has huge leverage for us.
Hey David, do you think, is garbage collection impractical because of C++? And would you use a high performance C++ GC if one would be available?
I think it's mostly a question of memory overhead. The RAM, right, 5 or 10% RAM cost at scale is a lot. One of the frustrating things is that there are lots of parts of the system that would be fine written in a garbage collected language, but there's also a huge cost to having a single system written in 2 programming languages, right? And you have 2 different sets of developers, and you build something thinking, oh, I can do this in the garbage collected sphere, and then suddenly that turns out not to be the case, and you wind up torturing the architecture because of that. Of course, the latency issues are important as well. And once again, if you pay 5 or 10% for the real, over a conventional GC for real-time performance, then that costs a lot.
All right. Thank you very much. Thank you, David.
Thank you.